let's learn to code diffusion a bit more, diffusion models. So you can watch this diffusion from scratch if you want, but it's not obligatory because we will anyways be learning this stuff. So thing with diffusion, you can generate images, but also text. So text with diffusion models, it works a bit worse than autoregressive transformers. But diffusion models are processing continuous data, like images. There are many different types of images. There is no like 200,000 images in the world and that's it. Like there is 200,000 tokens. There is infinite amount of images. So that's why we use diffusion models for infinite continuous data. So we can interpolate between them. So there is an argument to be made that now we can use diffusion and we can put images and text together. So we can use different tricks to make text continuous as opposed to discrete tokens. We can use like sentence embeddings, like whole sentence is a concept, so there is infinite amount of sentences and stuff. But the main idea is we can do early fusion. So we just mix image and text data and do diffusion on both of them. So this would allow model to natively learn both image and text. So in the current visual large language models, they just stitch together visual and text. So they stitch together and there is no too much connection. It's not natively trained like a single neural network, a single transformer. So maybe with this, when we train it together, images and text from scratch, everything is intertwined. It will learn more. It will learn everything in the same embedding space. It will learn physics and real world from images in videos, and it will learn to communicate, to speak from text, and it will also learn more from text because we are embedding like sentences or ideas. So this is similar to large concept model by Meta. So that's why we're going to be learning diffusion. You will learn to train on continuous infinite distribution of data. When coding diffusion, we have this Linspace. So this is when we generate noise. So we would use different numbers in diffusion, but now we are just learning what these commands do. So this is 10% noise, 20% noise. So we create a Linspace from 0.1 to 0.2 and 5 different equally linearly spaced numbers in between. So from 0.1 to 0.2 and these three numbers in between, linearly spaced. So that's what Linspace does. So that's how we create noise. So for each, we are noising and denoising to generate this. You can learn more if you don't know what this noise is. You can ask ChatGPT, but for now, I'm just going to focus on these commands. So not about theory, but just code for now. And alphas is just, so this is how much noise we add to the image. And then if we say 1 minus noise, we get the percentage or the portion of the clean image. If we add 10% noise, we get 90% clean image. So that's how we create that's how we create alphas. So alphas is 1 minus betas. And betas is our tensor that we just created with Linspace. So then we have these alpha cumulative products. So alpha comprods equals this torch alpha cumulative products of alphas across this dimension, the first dimension. So input is going to be this alpha tensor alpha that we already have. And the output is going to be, so the first one will be the same. The second one will be first times second one. The third one will be first 3 multiplied. So we get the third one. So this is because to the first one we add 10% noise. And then we add next percentage, but to the clean image. So to calculate how much noise actually is, we calculate the first times second. So this is added not to the full image, but to the clean part. So that's why we need to multiply them. Then it says here we just take the square root of these alpha cumulative products. And then square root 1 minus alpha cumulative products. So we also need to calculate that. So y square root we'll figure out later, but these are the operations that we need. So why do we use square root? So this is adding noise formula. Here x0 is original clean image, and this, what is this epsilon? I don't know what this is, but Gaussian noise. So this is the normal distribution noise, sample from normal distribution between 0 and I. This character, this is cumulative products of this, I don't know, ChatGPT has some writing mistakes. Portion of clean signal preserved at timestamp t. Yeah, so this is the portion of the clean signal preserved at the current timestamp. Why square roots? Because we are scaling standard deviations, not variances. So the standard deviation. So I asked ChatGPT like 3 times to explain this variance stuff. I couldn't get it, but now I think I understand it better. So let's see. Suppose we mix 2 random variables. You have A, some signal, and B, random noise. Now you define a new variable. Y is 8 times, so this is 8 times that signal and B times that noise. You're linearly combining them with weights A and B. And by the way, this is one beauty of ChatGPT. You can ask same question a million times. You can say you don't understand. You can't do that with human professors. So you want to combine this signal and this noise, but you want to scale them up, down, bigger, smaller, depending on something. So now we will talk about these weights that are scaling this signal and noise when we are combining them. Goal. We want y to still be a normalized random variable, meaning that variance of y should be 1. This is because we want this data to live in a predictable range, like -1 to 1. So we want whatever y is, we want its data to be between -1 and 1, for example, or whatever the range is. So that's why we want its variance to be 1. So it can be 0 and then variance 1. Like 0 is the mean. So we actually know that A plus B is equal to 1. Because if you remember, as you remember before, we defined signal and the noise, and when they add up, we get like the whole image. So the whole image is composed of the noise part and the clean part. So it's 1. A plus B is 1, the whole image. So we are adding this weight and this weight. So how do we add some number, weight here and weight here, so that the variance of this is 1? If you don't get it, I just recommend you just ask ChatGPT. You screenshot this, you ask ChatGPT, but maybe you can follow as well. So the trick is that A squared plus B squared needs to be 1. And if A squared plus B squared is 1, and if A plus B is 1, then variance of y will be 1. So that's the trick. Let's try to see why we need to have A squared plus B squared equal to 1. This comes from how variance behaves when scaling independent random variables. So what does that mean? We know that variance of A of the clean image is 1, because the clean image can be 0%, we can have 0% clean image or 100% clean image, or anything in between. So 0%, 100%, that's actually 0 to 1. And same for the noise. We can have 0% noise, clean image, or 100% noise, completely noised. So the variance is 1. So, well, in this case, it can be like between -1 and 1. It doesn't matter. It's okay. So it's just important that the variance is 1 here and the variance is 1 here. It doesn't matter if it's between 0 and 1. If we can scale it to between -1 and 1, that's not important. So this is the formula that you need to understand. If you have some constant number and a random variable, variance can be only calculated for the random variable. Constant number doesn't have a variance. But this formula says scaling a random variable A, capital A, by constant a, little a, causes the variance to scale by a squared. So that's the formula. So we have, let's say, this x variable that is a normal distribution, so mean 0 and variance 1. So it can have numbers that are outside of this range, but these are the most likely numbers between 0 and 1 or minus 1. But anyways, if we say 3 times x, so we are not multiplying the variance with 3, we are actually multiplying the deviation, the spread, by 3. So the variance will be deviation squared, spread squared, 3 squared. Because look, it will be 3 times 0, which is 0, and 3 times 1, which is 3. So now it can, the deviation will be mean is 0 and 3 and minus 3. That's the deviation, but the variance is that squared, so 9 to minus 9. But the variable can still take values above 3 or 9 and below minus 3 or minus 9. It's just the variance of those and deviation of this variable. Anyways, this is maybe a bit complex. So the main point is we know that if we have a scalar times random variable, variance of that is going to be scalar squared, because variance is squared times the variation of the random variable. Now let's go back to this formula. So we want variance of this to be 1. And why do we want that? So we want the data to stay normalized. Diffusion models usually assume inputs, images or features have a fixed scale, often 0 mean and unit variance, which is 1. This normalization helps the neural network train stably and predict accurately. So this is showing you clean image and noise. And we want always sum of, so this is how much, so this determines how much of the clean image, how much of the noise. And we always want the sum, the total, whatever we get, its variance to be 1. Basically, we want all of our numbers that go through the neural network to be between either 0 and 1 or minus 1 and 1 or some nice range like that, usually those two ranges. And there is no like super huge or super small number. So we want to put all of the numbers between, we want to stretch them or squish them to be between that range. This will make training more stable and easier to compute, and there won't be vanishing gradients or exploding gradients problems. When you multiply big numbers, they're going to become very big, or when you start multiplying small numbers, they're going to become very small. So we need to, and then maybe the precision, GPU doesn't have enough precision to have those numbers in memory, so it will maybe cut important information. So we want to put them in this range where it's safe for GPU to put it into memory where it can represent it. So let's see, we have this formula. So this is going to be equal to a squared times variance of a, we just explained why, plus b squared variance of b. And we know that variance of a is 1 and variance of b is 1 because as I said, the image can be like 100% noise or 0% noise, somewhere in between, and 100% clean image and 0% clean image, somewhere in between. So we can scale that also to minus 1 and 1. But basically we know that variance of this is 1. So this is just then a squared plus b squared. So we want a squared plus b squared to be equal to 1. As you remember in the beginning, we have, for example, a to be 0.1 and b to be 0.9, and they add up to 1. But we don't want a plus b to be 1. We want a squared plus b squared to be 1. So because we are just adding, we have just a and b, and we are not using a squared and b squared in our formula, we are just using a and b. We want to get square roots of this and this. So we will get square roots of this and this. and we will use those square roots in the formula. And we know that if we squared those square roots, we would get this and this number, which would add up to 1. So that's how we know that we will preserve the variation. But we will not use these squares in the formula. We will just use their square roots. So if that was complex, don't worry. I will try again with examples. So this is our formula. We get A times clean part plus B times noise. But we need to understand that A squared plus B squared must be equal to 1, because I explained earlier why. So this cannot be 0.8 and 0.2, because then those square, when you square those two numbers, that wouldn't be equal to 1. So actually, we need to take square root of 0.8, which is this number, and we take square root of 0.2, which is this number. And now, if you want to check if A squared plus B squared is equal to 1, we can just square those numbers and see, oh, okay, so this is equal to 1. Okay, so these are good values for A and B, because their squares are equal to 1. So that's why we're going to choose these values for A and B. So if you remember, in the beginning we have some alpha, which is how much noise we add, and the betas, how much the clean image. But alpha is not actually how much total noise there is. It's just how much noise we add to the clean part of the image each step. So to calculate how much actual noise there is, we will multiply. You see, for alpha, we will multiply all of the previous alpha versions. So the first alpha plus times the second alpha will give actual amount of the clean image. This is clean image. So we have this alpha cumulative products. So this shows actual amount of clean image, first step, second step, third step, etc. So these are going to be our actual values. And 1 minus this will be values for the noise. So let's imagine that there is no square roots here. So we just have the amount of the clean image in the current step times this clean image. This is scalar. And then this amount of the noise, which is 1 minus clean image amount, times the noise. This is scaling the noise. But as I said, this squared plus this squared needs to be 1. So that's why we need to just add square roots of both of them. So their squares are 1. So each sample xt stays normalized with variance 1, making training stable. And not just the stable training, not just that. So let's see another reason. Say you want 70% signal and 30% noise. Then you would say 0.7 times the signal image, 0.3 times noise. That doesn't work because variance doesn't add linearly when you scale a random variable. Variance of ax is a squared times variance of x. So you would accidentally be making something that's shrinking. It's too little, you are shrinking the image. Now, yeah, we are shrinking the total amount of combined cleaned image and noise. Here is an example. It might help you, it might make you even more confused, but it is what it is. Let's go. Let's take pixel 5050 from a grayscale 28 by 28 image. So let's say this pixel has the value of 0.6. So this is the gray value, just this value. This is the color. You run diffusion step with noise multiple times. Every time you add a bit of noise, maybe it can go from 0.6 to 0.57, 0.61, 0.63. So you see it's changing a little bit, but not too much. So actually, even if you add some noise, because it's not too changed, maybe it will still be part of the, like this pixel will still be part of some lines or shapes, and you will be able to recognize it because it's actually just a bit changed a bit. The spread of these values is due to noise. The spread is variance. So this is the spread. So this spread that we see here, this is the variance. So when we say 90% of the variance comes from the image, wait, okay, this was something else, ignore this. We mean the pixel values across these noisy samples don't jump around much. They're still close to the original image. Yeah. Okay, so 90% of the variance comes from this original value, and 10% comes from the normal distribution noise. Yeah, okay. Now it makes sense for me as well. This is important. Every pixel in the image is going to be changed during the diffusion process. Each pixel is modified by mixing it with random noise, and this happens independently for every pixel in every time step. Let's see an example. Let's see you have this image. So this is just grayscale values. Let's say this is dark, maybe close to black, this is close to white, and these are in between. Then you generate random noise. So it's mean 0, standard deviation, or variance 1, sorry. So 0.3, minus 0.8, etc. And do the forward diffusion step. So let's say square root of AT is 0.8 and minus this square root is 0.6. So these don't need to add to 1, their squares need to add to 1. So this is okay that these don't add to 1. So let's do this pixel by pixel. Follow the formula. So 0.8 times 0.2 plus 0.6, which is this, times 0.3, which is the noise. That's the first pixel. So you see, first the noise is random, and then the amount, how strongly we apply, that's not so random, we determine that. So we do less noise in the beginning and more noise later. So this happens at every time step. So we have just this code. This is Python code, square root of all alpha cumulative products of step t times clean image pixel. The same formula. And in the reverse process, so this is the reverse. This is a new thing we are learning. Now we start from the ending, from full noise or very noised image, full noise in this case, and we try to predict the previous t-1, the previous time step of the noise. So the previous image is going to be function of the current image and predicted noise. So you will just subtract predicted noise values from the current image. It's just one minus here. This also operates per pixel. That will be it for this video. In the next video, one of the next videos, I'm thinking of implementing this transformer with diffusion, so maybe training it as well. So they stopped using UNet with diffusion and instead are using transformer with diffusion. That's the new thing, because transformers scale a lot more predictably, a lot better than UNet. This might be the path towards general intelligence, or even more than general. So we will learn more about this diffusion, and it's very promising for continuous data training, and our thoughts could be continuous. So we'll learn more. You can subscribe to my channel and check my videos here. See you in the next video.